Welcome everybody to our webinar, a joint webinar of Flanders Make and imec on how to establish a predictive maintenance strategy. So before we start this webinar, there are some practical guidelines for those who are not familiar in Teams. So there are two features, chat room and raise hands. Please use them later on in the Q&A session at the end of the webinar. And we invite only speakers and invited participants to turn on the microphone and camera. So please switch off your camera. Okay, today we'll talk about the predictive maintenance, how to establish the predictive maintenance. It's a result of the project called Smart Maintenance Living Lab. And this project was started in 2018 and is ending soon by the end of the month. And in this project, we want to demonstrate the technologies that we have developed in the past. And thanks to the co-financing of Flanders Make, imec, and VLAIO, the Flemish Agency for Innovation and Entrepreneurship. This is our program. So, first of all, my name is Agus Mian Portogion Pusunggu. So I will be moderating this webinar and also presenting the technologies of Flanders Make. So I will give you some introductions why we need to do this maintenance and how we should do that. And then there will be interactive demo for 5 minutes. So we will let you play our demo. And then I will continue with my presentation on the technologies of Flanders Make on edge hardware, domain knowledge, signal pre-processing, and artificial intelligence technologies for rolling element bearing health monitoring and predictions. And then before we jump to the next presentation, so we have a break with some exercises. So you can challenge yourself whether you are better than the AI technologies that we have developed. And then my colleagues from imec, Sofie van Hoecke and Bruno Volckaert will give their presentations on cloud computing, artificial intelligence, and dynamic dashboard technologies for scalable rolling element bearing health monitoring and remaining useful life predictions. And then to conclude this webinar, we will show you the project video, and then there will be some company's testimony, and then and then we have a final session Q&A and some extra information. All right, so why do we do this maintenance? So the ultimate goal of maintenance is to achieve zero downtime. And how to do that? So we need to improve the asset uptime and maximize the asset lifetime. And there are a number of maintenance strategies already implemented in industry for years. And here I just show you the two maintenance strategies being preventive maintenance and predictive maintenance. As you can see that the preventive maintenance strategy is still dominating in the industry, and the predictive maintenance is gaining more attention. But if you compare to the predictive maintenance implementation is still limited. This is a survey between 2017 and 2018, and then the reason why the implementation of the predictive maintenance is so limited, as you can see here, are the challenges. The major challenge is the lack of resources, staff, and then the second one is the lack of understanding or new maintenance technologies, and so on. And if you cluster them, so we can have, let's say, issue from the management point of view, and then the issue from the technological point of view. So this webinar is not to give you how we tackle this from the management point of view, but we try to tackle this from the technological point of view. And of course, there is a link between the technological point of view and the management point of view. And in 2017, PricewaterhouseCoopers and Man Innovation released a report, and they classify the predictive maintenance into 4 levels. The first level is about visual inspections. That's the simple technology that we can use for PDM. And then the second level with instruments, with some interpretation from an expert. And then in the third level, more complex, more technologies. So we use real-time condition monitoring system, but still the interpretation requires some expert knowledge. And then the fourth level, which is called the PDM 4.0, that's equipped with predictive analytics to have more objective decision making. And a survey in 2017, so on 280 companies in Belgium, Germany, and the Netherlands, as you can see that the majority of these companies, they still implement the PDM with basic technology, the instruments with inspection, so periodic inspection. And yeah, only 11% of these companies already implement predictive analytics, so it is very limited. And yeah, from what we experience working with companies, so we noticed that many companies, they struggle actually how to jump to predictive maintenance. That's why it's very important to have a systematic methodology that can guarantee a success. So that's why do things right the first time. And from our experience, we have already a way of working where we the first step is to do criticality analysis, because this is strongly linked to the business case. So in order to do this in objective way, we need some data, for instance, maintenance record, this is important, production data, engineering data, logistics data. Based on this data, we have a way how to analyze them, and then we can determine the critical assets in our production plant. And then we also need to identify the failure modes. Why? Because the failure modes help us to identify what kind of technologies we need to use. On the market, there are a number of technologies, but yeah, we have to be selective there. So to make sure that there is a trade-off between the cost and the benefit. And yeah, so what we could do, so we can do market study to identify the set of practice technologies in terms of hardware and software tools, and probably the technologies available on the market are not available for our use case. That's why it's good to also approach this from the state of the art by contacting R&D organizations like vendors make on imec or maybe other universities. And then once we identify this, we can define required technologies for our use case. And then once we know what technologies we require, and then we can do a feasibility study. So we select sensors or data acquisition platform, edge platform, cloud platform, for instance, and then with software tools, we evaluate them. So on real case, and then at the same time, we can also do personal training, knowledge transfer, because as I mentioned earlier, lack of understanding is also one of the challenges in implementing predictive maintenance. And then once we do this exercise, we can check whether it is feasible, right? It brings added value to our organization. And yeah, so as I said earlier, at the end of this webinar, there will be a company testimony. So this actually reflects what we have done together with the company with this way of working. Okay, in this project, we selected a specific use case, in this case, rolling element bearings. Why? Because for those who are familiar or who have been working in the maintenance, so rolling element bearings are one of the most critical components in the industry. That's why the cost benefit is evident there. And in this project, we built this infrastructure, hardware and software, so we can perform tests in a reasonable time, and then later on we can do predictive analytics. So, right. Through this project, basically we create an open ecosystem. So where different organizations from different sectors, research and development organizations like Flanders Make and imec, and then technology provider like a sensor provider, edge computing platform provider, and so on, and maintenance service company who provide service to the end users can collaborate, and of course the end user can also interact through this smart maintenance living lab, because there are some companies who want to do maintenance themselves. Think they can also benefit from this. Right. So what's in it for you? So basically, yeah, we have this infrastructure, so we can perform customized testings. So if you develop technologies related to, in this case, bearings, so you can come to us. You can test your technologies, and then we also have this low-cost edge hardware. So if, for instance, if you want to test, in your production plant, for instance, so we can bring it to your production plant. We can acquire data and so on. And also we have open algorithms, so we know how these algorithms work. So we can also tailor these algorithms to your specific applications. And then we have this cloud service and machine learning models to make to transform data to actionable information, and then we can visualize these actionable informations with our dynamic dashboard. And yeah, we will present this in more detail about the edge computing and also cloud computing technologies in the next presentations. All right, so now it's time for the demo. For those who have mobile phones or tablets, so you can scan this QR code, and then it will direct you to the to the website. For those who don't have mobile phone or tablet, you can also copy paste this link and then put it on your browser, and then I will go to the browser. Right, so this is the demo that we have built in this project. So yeah, this demo basically uses real data, but because we have limited time in this webinar, so basically we accelerate the data acquisitions. So as you can see that here we have three machines that we monitor, and this basically this dashboard is dynamic. You can modify, you can personalize your dashboard according to your interest. But for this purpose, we disable that functionality, because just to avoid problems, because I think there are about 150 participants joining this webinar. So as you can see, so from raw data, we have transformed this into actionable information. In this case, we have two actionable informations. The first one is the health index. As you can see, the health index really gives you a quick understanding what's going on your machines. And so it is a value between 0 and 1. So if the value is 1, so it means your machine is still healthy. If the value is decreasing towards 0, so it means your machine is degrading. And as you can see that, for this one is already red, so it's going to fail soon. And then this is still orange. It's degrading together also with setup number 7. And then we also have another actionable information, remaining full life. Right, so you please have a look. And another thing that I want to mention, that when there is onset of degradation, so what does it mean? It means that when the degradation starts, so we release this breakpoint. So the breakpoint or the onset of degradation is detected. And as you can see that, and then an operator can take a look what's going on actually, and then they can also check this breakpoint for different machines. In this case, yeah, and then you can take a look in more detail. So at different tabs here. All right, so yeah, so please take a look. So this demo is still running in the back end, but we will come back later on this demo during the break session. Okay, so now let's move on to the next presentation. Sorry. All right, so it's about the technologies on the edge, hardware, software for rolling element bearing health monitoring. And this is actually the edge cloud architecture that we have implemented in this project. So as you can see, we have 3 layers. So the bottom layer, and then the middle one, and then the top one. And what is important here actually at the bottom layer, the latency is very important. So it's very sensitive. So ideally, to avoid data corrupt, the latency at the bottom layer should be 0, right? And then at the top, at the cloud level, so the latency is not very an important issue. So okay, so we have our edge devices mounted on the critical assets to collect raw data, and then we have the second layer, the edge computing platform. So this platform can also perform control, real-time control to our assets, and then storing raw data and manage the data, and then perform data pre-processing. And then once this data has been pre-processed, we push them to the cloud for data analytics to visualize actionable information. Okay, this is the lab infrastructure that we have established in this project. So we have, yeah, we have, let's say, brand new bearings, and then we install these brand new bearings on our infrastructure. So you can imagine this like fleet of machines, identical machines. And then we have developed methodology in the past to to accelerate the lifetime of bearings in reasonable time. So ideally, in working day, we can finish the test because the test duration is proportional to the test cost. So as you can see, that the average test duration is about 3.6 hours. And yeah. At the edge, it's important to select relevant technologies, relevant sensors. That's why imposing domain knowledge is very crucial there, because if we select wrong sensors, it will propagate to the end, and basically we will capture nothing, and then we have an issue. So based on our experience, our understanding of machines, so we have, for these specific applications, we have imposed some requirements, the dynamic range of the sensor at least 50G, and then the frequency bandwidth at least 10 kilohertz. And in the previous project, we have selected low-cost MEMS accelerometers. So it's around 57 euro per unit, while high-end accelerometers, piezo-based accelerometers, you can find them on the market at, I think, approximately around 150 euro per unit. But bear in mind that the high-end accelerometers requires specific signal conditioning, which is a lot more expensive than the signal conditioning for low-cost MEMS accelerometer. And then on the edge computing platform, we have defined the specifications. This platform is based on industrial PC and also equipped with acquisition modules, so we can control real time and also acquire data. For vibration data, we can acquire with a sample frequency up to 50 kilohertz. But for other signals like temperature, loads, we can typically acquire at the sampling frequency of 1 kilohertz. Right. So, okay, we have the sensors. We have data acquisition platform at the edge. Now we need an algorithm, a robust and reliable algorithm to transform this raw data to useful information. And here, based on our physical insights, we have developed an algorithm to pre-process vibration data. So as you can see, that vibration data is very complex. It's a result of different machines. In rotating machines, you can find a lot of machine elements, bearings, gears, shafts, screws, and also random noise, for instance. And typically, bearing related signal is very weak compared to the other signals. That's why you need certain signal pre-processing steps to ensure that you acquire, you extract information related to the bearing faults. Yes, and then we have benchmark our algorithm with the state-of-the-art methods some 2 years ago. So as you can see that, of course, this is the artificial fault, because we had to do that because we want to quantify the fault. So we needed to introduce artificial faults there. So as you can see that with our algorithm, we could detect early fault, in this case about 200 micrometer, while the current state-of-the-art method, we could detect only fault of the size of around 500 micrometer. Okay, so we collected raw data. So typically, this raw data has about 100,000 data points. So, and then we acquire it periodically or maybe continuously, depending on your applications. And then we need to transform this data with the algorithms that I presented earlier to extract features or health indicators or condition indicators, right? And then, in this case, so we transform from 100,000 data points into only 6 values per acquisitions. And then for an expert, this is already information because they know actually what's going on here. But for non-expert, it's not evident, it's not obvious for them. That's why we need to transform these features or condition indicators into actionable information. Then we apply AI-based feature selection and transformations, and now we have this health index, which is obvious for human. So it's easy to interpret. So health index, a value between 0 and 1. If it's about 1, so it's still healthy. If it drops, then it's degrading, and then we can define color to indicate it is healthy, degraded, or faulty to replace. So once we have this, an operator can easily take an action. Right. So now the questions. So can we implement these, let's say, these AI-based data transformation or data analytics at the edge layer? The question, possibly, but this is not optimal because what? As you can see in this architecture, the edge computing platform only acquires data from 4 machines, right? So in order to build reliable and robust, AI-based, let's say, decision making, so you need certain amount of data, of course, and you don't. But if you apply it at the edge level, maybe you need more time to deploy your model. While if you apply the AI at the cloud level, so basically you observe all your critical assets, and then you can deploy your model quickly. And then this brings me to to conclusions. So my colleagues from imec will present about this approach in the next presentations. But before we go to the next presentations, and we have interactive exercise, I guess you still open your browser, and my colleague can already post 2 questions in the chat.
Yes, it's okay.
Yeah. Okay, so please, we still have some time, So, yeah, we have 4 minutes before we jump to the next presentation. Yeah, maybe I can also show the browser. Yeah, you can zoom in, zoom out. This is about the health index and also the remaining full lifetime. You can zoom in, zoom out. Yeah, so as you can see that maybe the first question, which I think this is obvious from the graph, which machine, the breakpoint is detected first. I guess you can notice that. So setup number 4, the breakpoint was detected earlier compared to the other machines. And then the second question, which machine? So now we have 4. Here we have 3 machines. So the second question, which machine will fail first? So this is already faulty, but it doesn't fail yet, right? And then, okay, this machine is still okay, it's still orange. So please make your predictions. So which machine will fail first? Okay, you can also take a break. So in 2 or 3 minutes, we will continue with the presentation from our colleagues of imec.
Okay, I think you can go on.
Yeah. Okay, so I will then stop sharing. And I hand over my talk to Bruno and Sofie.
Okay, thanks. I am Bruno Volckaert. I'm a professor at the University of Ghent, affiliated with imec. Me and my colleague Sofie van Hoecke, who's also a professor at Ugent, will be talking about the cloud-based data gathering we did in this project. and Professor van Hoecke will talk about the machine learning and the dynamic dashboard. Now, August-Mian already mentioned the part that Flanders Make did in this living lab, namely, among others, they designed test beds where wear and tear of bearings could be evaluated. Now, these test beds, they generate data, and this data, this had to be ingested into, in our situation, a cloud-based backend. You can see that here in the middle. So all this data from the 7 different test benches was being absorbed in a cloud-based backend. Now, on that data then, machine learning and a dynamic dashboard were developed. Now, I'll first go over what we did exactly in that cloud-based backend. And looking at it from a high-level view, we can see here on the left-hand side of the slide that all these sensors, we treated them as producers of data. Now, these sensors, they produce what we call time series-based data. These are high detailed time series stamps alongside metadata of which sensor is the data coming from, which experiment is it coming from, and then of course the measured sensor event, a certain degradation that was, or a certain vibration that was felt on the bearing. Now all this data is being ingested, we call that ingested data put into the cloud, into a system that we named Obelisk. And Obelisk is imec's cloud-based scalable platform for IoT data ingestion. Now, you have that Obelisk in the middle. At the right-hand side of the figure, you can see that there's a number of different consumers there. And these consumers, they can be regular users just like you and me, or they can be applications, or in our case, machine learning applications, which are trying to establish when will this bearing break in the near future. So they all query that data from the Obelisk central platform. Now, the initial goal in the Smart Maintenance Living Lab was to ingest raw accelerometer data from each testbed. This proved to be unnecessary. So initially we looked at, we're going to be ingesting 50,000 events per second, which is what those accelerometers are pushing out per test bench into the cloud platform. This is possible, but it's not advisable. And I'll come back to that in a few moments. Now, if you put that data into a system like Obelisk, of course, you're interested in, is it actually going through? Is my data being absorbed? Is it being logged into the central cloud backend? And that's what you see here. So we have built a number of very developer-oriented dashboards, which are purely aimed at looking, is my data looking correct in the cloud backend? Is it coming in? Is everything going as planned, etc.? So you can see here timestamps. In reality, these are very detailed timestamps, geo hashes which specify the location where that sensor was located, which produced the data, some source IDs, and a specific value, and it's of course the value that is most of interest here. You can already also see that there's you need to be logged in to see that data, and there's specific scopes which you see here at the top right hand side, scopes which basically detail this is a kind of project, this is a kind of experiment. You have to realize there's a lot of different projects sending data at the same time towards that Obelisk backend. So let's dive into that a little bit deeper. What are the key aspects? And I already told you about we're ingesting data and we allow querying that time series data. What I didn't talk about yet is the fact that you have to be very security aware when doing so. You're working here with bearings of different companies, of different experiments that you're doing, and you don't want potentially competitors seeing the data of other, the experimental data of other companies. So you need to be security aware. You need to create some kind of data overlays which specify that sensor at that time the data can be seen by person X and Y, but not by person Z. So data isolation is very much a core asset here. It's also a system as a service. This means that Obelisk itself, it does not have to be installed on premise. It's up and running at all times at imec side, at IDLab, and you can use it as a service, just like you would use your Office 365 or anything else cloud-based. Other aspects is that it's very scalable. So I mentioned that we're having a lot of projects, smart city projects, these Industry 4.0 projects like the Living Lab. They are all being ingested into Obelisk. Now, for that, you need to be really scalable, because at times when there's no experiments, there might be a few events per second going in, but other times there might be 10,000s of events per second that you need to be able to ingest and to log and to persist. So you need that scalability. You need to be able to scale back when there's almost no load, and you need to scale up when there's very high load. For that, we designed and prototyped a microservice-based architecture, which is able to scale on demand. This is also not run on your typical run-of-the-mill desktops. This is, of course, run on highly powerful server hardware, which is actually present in iLab-T's test lab. It's very robust in that, well, you don't want to lose data. So you, in essence, have to make sure that all these things, it's a microservice-based architecture. In the back end, there's more than 60 services involved in ingesting and allowing to query that data. You need to make sure that no data is lost. So there's all manners of buffered ingests, there's failover mechanisms. We even have, in fact, 2 operational sites, so that if one would be down, electricity failure or so, another location can take over, ingesting data and offering that data to applications which need the data. From a very high level view, you can see that we have a REST API here, which securely allows you to send data over, and the data then, for one, the metadata is stripped and put into a catalog, but the other data is stored in long-term storage, which can then be queried, or you can even subscribe to have push notifications in case some interesting data is coming along. Under the hood, there's a large number of technologies which are being employed. It's microservice-based, so a lot of microservice-based technologies, container technologies for deployment, Kubernetes for orchestration, etc. If you're interested in such things, definitely give me a call. Now, very specific, what did we learn in terms of cloud-based data ingestion in this Living Lab? For one, we learned that if you have multiple experiments with competing customers, sometimes competitors, it can be very tricky to get your data viewing or access rights correct, especially if you retroactively, when the experiment has passed, add people to the project or remove people from the project. There's always a trade-off that you need to do. Either you will have very fast ingest times and you deal with who can view the data at query time, or at ingest time, you have to label your data and then the queries go faster, but there's always a trade-off, and you need to be you need to pay special attention to that trade-off. You also need to think hard about the granularity of your stored data. Like I said in the beginning, 50,000 events per second going into Obelisk. We later on moved away from that because the added machine learning accuracy was not worth it. And we drastically reduced the number of features that was ingested into Obelisk and had some edge-based local sampling or data reduction, which greatly improved the scalability that we could offer. My colleague, Professor van Hoecke, will now go over the machine learning algorithms.
Yes, indeed. As Bruno told you, we processed the data that was ingested in the cloud and applied machine learning algorithms on top of it and visualized the results in the dashboard. I will first dive into the machine learning, how we detect degradation and predict remaining useful life. As Guzman already told, there's a shift towards predictive maintenance, as it's the ideal trade-off between corrective maintenance, where there's a huge repair cost, and preventive maintenance, where we replace components even if they would not fail in the near future. So when shifting towards predictive maintenance, you can increase the equipment uptime by up to 20%. It additionally allows for optimally scheduling your maintenance plans. It allows to plan for spare components, but more importantly, you can see the remaining useful life and act upon that by reconfiguring the system to prolong component life. The definition of predictive maintenance in Latin or prognostics in Greek is that you determine the remaining useful life, and that's of course the scope of our part within this living lab. Prognostics and health management can be done in two different approaches. One is the model-based approach, where you use analytical or physical models to approximate components' behavioral and degradation. The benefit of the model-based approach is that it gives you high accuracy and is capable of simulating diverse scenarios. However, a big downside is that it's mostly used to model healthy behavioral, as the real degradation processes are stochastic and therefore hard to model. As a result of the increased use of sensors, data-driven techniques came to the forefront. These data-driven approaches or machine learning approaches, they are models that approximate the component's behavior and degradation via machine learning, with the benefit that no expert knowledge is needed and that the degradation and failures itself is inferred from the data without having even to specify the failure type. The state-of-the-art solutions require lots of data, feature engineering, and cannot deal with conditions that are not captured in the data, and that is what we will solve also here in this living lab. So the goal was to design health indicators and predict the remaining useful life, while being able to deal with variations in the setup, different bearing types, and different operational conditions. And we wanted to design generic indicators. We did a two-staged approach, and first we designed the health index, as already indicated in Ugent's part. We designed machine learning models to detect the degradation onset. The health index that we outputted from our models, it's a value bounded between 0 and 1, so it's easy to interpret, and it can be used as a threshold. And we expect apply monicity behavioral as the mechanical components experience gradual degradation and normally no recovery. For this health index model, we assume the first samples of the data as collected by Flanders Make to be fully healthy, and the last samples of the bearings that failed, we labeled them as unhealthy. And then we trained a weak model with only a few labeled samples to predict then for all the other samples. We did, of course, cross-validation across bearings to assess the generalization. Here you can see one of the sample results for one of the bearings, and as can be seen, the black dashed line, it pinpoints the moment where the degradation has been detected, and where the health index surpasses the threshold of 95%. From that moment on, where we detect the start of degradation, a remaining useful life estimation is made. For that, we have built a machine learning model that uses features derived from the health index, as well as some statistical and model-based features as input to our machine learning model. And it's a remaining useful life model with an unbounded target. The biggest challenge here was that we have unbalanced targets, more specifically gamma distributed targets, where we only have a few samples with very high variation towards the end of the run, which is of course just the part that is critical to predict. And therefore, we adapted our remaining useful life estimation towards a two-staged approach, where we restrict the train and prediction for remaining useful life based on the health index threshold. Here you can see again a result for one of the bearings, where on top you see the health index as predicted by our first model, and whenever the threshold is surpassed the dashed line, from that moment on you see a remaining useful life prediction is is done. We evaluated different approaches, and truncating the data sets to the degradation segments gave the best improvements for the remaining useful life. So to conclude, our prognostics and health management approach achieved the best results by truncating the data set to the degradation segment for remaining useful life prediction. We evaluated with all the bearings as collected by Flanders May, but also with public data sets where bearing degradation data was provided. And it was empirically shown that our solution is a good tool for getting insights into the degradation process of the bearing. And the machine learning results were beyond state of the art on multiple areas. We also learned that remaining useful life prediction is a complex and complicated process, and it's best to only start remaining useful life prediction when the degradation is detected. Thanks to the fleet, in this living lab, we had faster data collection and a more robust solution that could deal with variability. The best way to do remaining useful life prediction is having a mix of engineering expertise, physics of failure knowledge, and data analytics to make the decision making more robust. So I think here there's an opportunity to shift towards hybrid AI for remaining useful life prediction. And of course, besides having the machine learning predictions, it's important to gain insights into the degradation and maybe capture feedback on the prediction to optimize your models. And that's why we also designed a dashboard. And that's the second part of my presentation. We didn't want to use state-of-the-art dashboards, as there's a hard link between the data model and the visualization, and dynamicity is only achieved by implying lots of if-then-else rules. We wanted a dashboard that could visualize whatever you want without any upfront configuration. To do so, we provided every sensor with a web API, so you could do GET requests or just HTTP requests to the specific sensors. And besides returning only the value, also metadata was returned, as the sensors were also semantically described. So instead of only having the value, you also receive the metadata, like the type of sensor that is capturing the data, what type of data it is capturing, where it is located, and so on. We did not only do this for the sensors, but also semantically annotated every visualization widget and the different machine learning models. And then semantic reasoning is used to, at runtime, combine the data, sensors, machine learning outputs, and the according matching visualizations to visualize it in the dashboard. And this way we enabled, on one hand, a user-driven dynamic dashboard where the user can interact with the dashboard and select the data, machine learning outputs, or whatever he wants to see, and then the according matching visualizations are automatically provided. So the user achieves what he wants without the pre-configuration. But more importantly, when monitoring the bearings, whenever a start of degradation is detected, an event is thrown into Obelisk and captured by the dashboard, and then it appears in the list on the right. When the user clicks that event, an event-driven dashboard is automatically created for the specific breakpoint that is detected with the metadata, the health index overview, or the remaining useful life predictions. We also provided a possibility to capture feedback, so the user can merge related events, can relabel events to give more meaning to the event label, or he can delete if something wrong would have been predicted. That feedback is then again pushed into Obelisk and can be adopted by the machine learning algorithms to optimize them. This functionality is disabled in your dashboard purely for demonstration purposes. So to conclude the part of my colleague Bruno Volckaert and me, we presented how the data generated by the fleet that was set up by Flanders Make and the features they calculated, they were ingested into the cloud, which is an open, flexible and scalable architecture as presented by my colleague. And then that data is used by our machine learning algorithms that give an indication of the health of the bearing, and when the degradation is detected, the remaining useful life is predicted from that moment on. All the machine learning output, but also the features as calculated by Flanders Make can be dynamically visualized in our dashboard, and whenever a breakpoint is detected, also an event-driven dashboard is automatically generated. Both Obelisk as well as the dashboard are generic components and are not restricted to this use case. And now I give the floor back to Guzman.
Okay, thank you very much, Sophie, for your presentation, and also Bruno. Okay, so now we are approaching the end of this webinar. So I forgot to mention that we will share our slides after this webinar, but you should first fill in the evaluation form that will be provided very soon. Okay, I will again share my presentation. Okay, so again, to remind you what's in it for you, so we have infrastructure. We can perform customized testing. Then we have low-cost edge hardware, local data reductions, different algorithms. They are open, so we can tailor them to your specific applications. And then we have this cloud service with machine learning models, and then dynamic dashboard to visualize actionable information. And let me show you a video, a project video, to summarize actually what we have been doing so far.
In the smart maintenance project, we focus on health monitoring of rolling element bearings, which are one of the most critical components in the industry. To demonstrate that, we have developed open technologies platforms where we can select sensors, acquire raw data, and then pre-process the raw data, and then transform the pre-processed raw data into actionable information.
We're in the lab today with the setups that we use to test rolling element bearings. An example of one of these bearings is this inner ring. So we have 7 identical setups here that we use to perform accelerated lifetime tests. This means that we really try to degrade the bearing in 1 working day. During these tests, we try to capture as much data as we can. We capture the temperature data, acceleration data, and this all locally through a PLC system. And this PLC system then acts as an edge computing device where we calculate a set of features, and this set of features is then pushed to the cloud to visualize the data.
imec created the Obelisk platform. It's a scalable container-based cloud backend in which the smart maintenance monitored data and features are ingested. On the IDLab cloud environment, 2 machine learning models are deployed. One for the health assessment and breakpoint detection, one for the remaining useful life prediction. The health assessment is a prediction between 1 and 0 that indicates the health of the rolling element bearing. This prediction helps with 2 things. One is the breakpoint detection, and the other one is an estimation of the degradation rate of the bearing. Once a breakpoint has been detected, an event is generated and pushed back into the Obelisk cloud platform. From this moment on, the remaining useful life is predicted as the time in seconds until the bearing will eventually break down. This prediction allows to schedule maintenance and move from a preventive strategy towards predictive maintenance.
The Smart Maintenance Living Lab project creates an open ecosystem that enables companies from different sectors to collaborate. For example, R&D companies, technology providers, maintenance companies, or manufacturing companies as the end users.
right.
In the smart maintenance.
Okay, so now I will give a company testimony. So I expect Anirudh from Bosch. I don't know, Anirudh, if you are still.
Yes, Agusmian, please.
Yes. Yeah, so this is the testimony prepared by colleagues from Robert Bosch production plant in Tienen. So yeah, basically we have followed this way of working that I presented earlier. So yeah, they are currently working on a project of condition-based maintenance on fast-moving linear axis. So with vibration analysis, they want to detect and predict upcoming problems with tooth belt, gearbox, bearings, and so on. And yeah, so we set up these collaborations. So they new vendors make, and then yeah, so we really follow this workflow. So now we are in the feasibility study, and yeah, hopefully the feasibility study shows that it is feasible to implement condition-based maintenance or predictive maintenance in their production plant with high success rate.
Yeah.
Yeah, I don't know. Yeah, if you have additional remark about it, Anirudh.
Right now, no. Only
Yeah.
thing is that we are working with the linear bearings, like you had worked with the rotary bearings before. Now that we are working with the linear bearings, hopefully we make good process through the project finally. So yeah.
Okay, thank you, Anirudh. Okay, so now I don't know if there are still open questions. So I think some questions have been answered. And just for your information, so we noticed that some participants indicated their interest to have one-on-one follow-up discussion. So we will, after this webinar, we will contact them, and then yeah, we will have some further discussions and how to proceed further. And for your information, here there will be another webinar coming up in June 10th. So this webinar is a joint webinar between VLAIO and series. It is in the framework of AI Research Flanders. And yeah, the theme of this webinar is AI-based smart monitoring and health management of industrial assets. So please stay tuned. So yeah, we will send you the invitations in the near future. Okay, so for further details, so if you want to have a specific discussions, different topics, so please contact us through these email addresses. Yeah, we are very looking forward to talking to you again in the near future.
Agusmian, maybe we can have some time to take a look at the questions in the chat, because I think there are still some questions unanswered for now.
Okay, so indeed, yeah, I think we still have some time. So indeed, let me see what kind of questions still unanswered.
I think, for example, Chris Rosa had a question. Do I understand correctly that for real-life applications we would need to install permanent accelerometers and PT100s at all components we want to track? It's there in your screen, yes.
Yes, so indeed. So the first question, do I understand correctly that for real-life applications we would need to install permanent? Yes. So for very critical assets, we need to permanently install accelerometers because yeah, if things go wrong with these critical assets, so yeah, it will lead to a disaster, to very serious problem. So permanent installations is recommended there. That's why yeah, low-cost solutions is yeah, it's interesting for these applications. And this temperature sensor, from our experience, temperature has also an effect to the to the vibration manifestations. So it is also advised to have temperature measurement available if the temperature varies quite differently. But if you know that in your application the temperature varies very little, basically you don't need this extra information. That's okay. And then I think Bruno already answered some questions.
Yep. Yeah, that's the next one.
Yeah, and then how would you cope with variable conditions? Yes, that's actually related to the previous question. So indeed, in practice, the operating conditions can change. That's why we need also to acquire other operational parameters like load, speed, and temperature, and then combine them with the vibration sensor, because these operational parameters also affect the vibration manifestations. So since we are interested in detecting and tracking the health of bearing, not tracking changes due to the changes of the operating conditions, that's why we need to take them into account.
Can I add to that?
Yes, please.
Yeah, we tackle it in different approaches by building generic models that are trained on data from the different operational conditions, but you can also build specific models for a cluster or one specific condition. And then if you have new operational conditions, you can start from either the generic model trained on a broad set of conditions or from a nearby condition. This is calculated automatically as the distance between the different models and conditions, and then apply transfer learning, incremental learning to tune towards this new condition by only needing limited data for that new condition.
Yeah. Thank you, Sofie, for the clear answer. And then there is another one. How about auditive predictive maintenance? I'm not sure if I understood, but I think this is related to if we use acoustic measurements. So if there's a case, yes, so acoustic measurements can also be used, but from our experience, probably the acoustic, based on our experience, probably we cannot detect early faults with acoustic measurements. So probably when the fault is already quite not very severe, but maybe medium, then we can detect that with acoustic measurements.
I think related to that part, we already had an European project where we collaborated with Philips Drachten and used acoustic data to do early fault detection. And now Vlaanders-Meek and imec will jointly collaborate in the ICON ACMON, where also the potential of acoustic data is investigated for predictive maintenance. So if you're interested, you can let us know, and then we keep you updated whenever there are ACMON outcomes and there's events in that area.
Yes. And then another one, two approaches were mentioned: analytical, based on physics, and machine learning, based on your experience. What are the false positive rates of each approach?
Well, I think.
Yes, please go ahead, Sofie.
Yeah. The model-based approach, it has the benefit that it models using mathematical formulas and whatsoever. So whatever is modeled, it works correctly, but it's easier to model the healthy behavioral than degradation, because the degradation is more unpredictable. And that's why we see today the analytical or model-based solutions are mostly used for normal and healthy behavioral, where the machine learning, it just derives patterns from the data. And with the downside sometimes of being black box, and if it's not in the data, you cannot derive it. So I think if you combine both strategies and improve the machine learning with the physical knowledge, the predictive performance of the machine learning will increase, as it doesn't have to learn what is already known. So if you, but to make a bold statement on the false positive rate, if you look at the degradation and you only modeled healthy behavioral, the data-driven approach will clearly outperform the model-based solution. If you want insights into the decision-making, the model-based, especially in the healthy part will outperform the data-driven one, and that's why the collaboration between both is that powerful. And yeah, recent research trends are also investigating, especially also in our team, on this hybrid AI, where you take best of both.
Yeah. Yes, I agree with you, Sofie. Thanks a lot for the clear answer. Yeah. Any more questions?
I think there is still one from Vital Driesen Guzmian. Is 100% data learning possible?
Yeah, this already answered by
okay,
Sofie. Yeah. So indeed, so combination of physics with data-driven is always better based on our experience.
Okay, then I think we can finalize.
Yes, so okay, so thank you very much for your attention, for attending this webinar. Yeah, we will send you the evaluation form, and then you will get the slides of these presentations. Hopefully by today. Am I correct, Dries? So we will do our best. And also the video of this webinar will be shared to the audience.
And that's it.
Yes. Okay, so thank you very much. So yeah, we will then possibly talk to each other in the near future. Thank you and have a good afternoon.